So that link, I put that link in the module, oops, wrong class, in the module from Tuesday, and I also put it up under the shared or the other resources. So that's just there as a little bit more information. It doesn't change how we calculate it. It's just a little more context to that kind of problem. So that was the end of 6.1. So 6.2. So I mentioned on Tuesday, and I forgot to squish these together. There are lots of different applications for integrals. We talked a little bit about probability distributions on Tuesday, but that's just a little bit of FYI. What we're actually going to be covering in this class are these two. Three, technically. So we'll talk about continuous income stream and consumer surplus and producer surplus. So most of section 6.2, the work when you're doing these problems is knowing what formula to use and knowing what to plug in where. So we're going to have a few different formulas in this chapter, none of which you need to memorize. You will be provided the necessary formulas on your test. But it's just knowing which formulas to use. So we're starting with the continuous income stream. And we're going to look at one brief example that we don't need calculus for, and then we can take that and generalize it to a calculus concept. So suppose you make $15 per hour. This is going to seem a little weird for now, but your flow rate of income is going to be, I'm just going to call it f of t, is 15. So the rate is $15 per hour. So your income is coming in at this rate of 15. And so if we were to graph that 15, it would look like this. Probably not going to go forever. You're not going to work infinity hours, but we can let t be however many hours we're working. So for example, if you work 40 hours, of course your income will equal 15 times 40, which will be 600. So we know how to do that. $15 an hour, 40 hours, we just multiply them. But if we were thinking about that on a graph, our flow rate being the function, so that's 15, we're making $15 per hour consistently. We have this area is equal to 15 times 40, because we have 15 on the y-axis, so the length of this rectangle is 15, the width is 40, so the area is also equal to 15 times 40, which is 600. So even though we're not talking about area here, income is not area, we can get income by multiplying our per hour wage by the number of hours. And visually that turns into a rectangle. But really it's just sort of this thing that we get from multiplying two things together. $15 an hour and 40 hours. So we can do that without calculus, although we might notice that the area under that curve at 15 is the integral, that should be a t, from 0 to 40, because that's the x, or the t in this case, that we're integrating over. And we can get that without actually doing the integration since it's just a rectangle. So we need calculus if our flow rate is not constant. In this case, we just had a constant flow rate, so we had this nice rectangular shape and we could just multiply the rate times the hours. But what if the income stream is changing over time? Then we're not going to have a nice rectangle and we can use calculus. So the definition here and the formula for total income. Oops, whoa, I don't know what I just did. Okay, we're fine, sorry. So this is also on page 394. So if f of t, so we're going to be using t because the flow rate is going to depend on time. So if f of t is the rate of flow of a continuous income stream, then the total income produced during the period from t equals a to t equals b is just the definite integral from a to b of that flow rate f of t dt. So if I'm just going to draw a quick little picture. So if we had an income that was not constant, maybe it's something like this, it's just sort of a random curve. And our time is A to B. The total income is represented visually by the area under this curve because it's that rate of flow, just like our $15 per hour above, times the time on the bottom. So this is the formula. It's just a definite integral, which we've been doing for a few sections now. So let's look at an example of how we would apply this in a situation where this would actually happen. So I'll give you a moment with this example.
It's noisier at your office than it is at your house. Yeah.
Yeah, that's actually not surprising. I can, Marcus has the office right next door to me, and I can always hear him during.
Right.
Yeah, he's pretty loud.
Has a voice that carries.
Yeah.
Okay. So here's our example. The rate of flow in dollars per year. So instead of like dollars per hour, like we would earn a wage, we have dollars per year of a vending machine over a 5-year period is given by this function. So we want to find the total income produced by the vending machine during the 5 years of operation.
So would you do 0 to 60? Or would you do 0 to 5?
0 to 5. And that's a good question.
Okay.
So the hint of what our units should be is that they should just match. So our rate of flow is in dollars per year, and our time is in years. So those two units of time should match. So the integral that we're setting up is just going to be just like the formula above. So this is 5 years, so we're going to start at 0 years and go up to 5 years. So that's the operation time of this vending machine. Our function is 2500 e to the 0.05 t dt. And that's it. So again, for chapter 6 stuff, you can use technology to calculate these integrals. So,
14,201.27.
Okay, let's look at that. That sounds right. Oops, 2500 e to the 0.05 t. So 14,201.27. So since we're talking about money here, we will always just round to 2 decimal places. Blah. So that's it for that one. We're given this function. We're looking at the 5-year period. So we're just starting that time at 0 and going up to 5 years.
Doesn't E usually represent like rate of natural growth?
Yes, or decay.
So how does that relate to a vending machine?
So I am just going to graph this function. I am struggling to get a reasonable graph on here. Just a second. So E is used to model a lot of different things. So it is used to model growth, like investing at a continuous compounding continuously, which we're going to see in just a moment. It can be growth in the natural world, like growth of populations. It can be all kinds of growth. And so it's used to model all sorts of things, even things that we wouldn't necessarily think of as exponential growth, especially when we're looking at just a short period of time. So like here, it specifically is saying that the income of the vending machine is modeled by this function for the first 5 years. So it's really just these first 5 years that are fitting this growth. If we zoom way, way out, then we're going to see this function. And of course, the vending machine isn't going to be like super, super lucrative in 100 years. So this model is really only fitting the vending machine for a short period of time. And a lot of times models do that. They'll like fit just a little bit and not the whole thing. So it's entirely possible that there could have been a different kind of model that fit this particular vending machine. But it's not necessarily growing exponentially. It's just for a little bit.
That was a good question.
It is.
I bet if you put gold in there, it'd do that.
Probably
Or maybe it just got stolen.
okay. So this is just this straight continuous income stream, but we actually have one more layer to this, which is the future value. So what if we take this vending machine and then automatically put the income from the vending machine into like a savings account that is compounding continuously. And so we're going to look at what happens if we invest this income immediately as it comes in. Which is future value of a continuous income stream. So a little reminder, we haven't actually talked about this in this class, but you've probably seen this before. So this is going to be a thing where E is really doing its thing. So continuous compound interest has this formula. So this means if we put some principal amount or starting amount into an account that's compounding continuously, that means the interest is being calculated all the time and it's adding to itself. And we have R is our interest rate. And T is time in years. So A would be the amount after T years. So this is the standard classic continuous compound interest formula. So E in this case is the same E. And this is a full exponential growth model. This completely fits that. If we could leave our money in this account forever, it would continue growing exponentially forever. So the question we're asking here, though, is we have a continuous income stream. So we're not just putting one principal in and then leaving it for a long time. We're going to be continuously adding money to this. So in this section for the continuous income stream, the principal is now going to be that continuous income stream. We have to make a little bit, we have to change a little bit more of this formula also, because this formula assumes that we're putting money in and then leaving it for T years. However, the first part of our money we put in will be left for a long time, but then the money we put in a year later is going to be left for a year less than that. And so the time that all of this money is in the account is going to be less and less the later we put it into the account.
Real quick, Madeline,
Yeah.
that continuous income, the little bracket, is that supposed to be just on the P, or is that supposed to be the whole equation, the continuous income stream?
Just P.
Okay, thank you.
Yep. So the E is just the part that's saying this is growing a bunch. The R is fixed, that's the interest rate. And the T is the other thing that we have to deal with a little bit. So I'm going to scroll down to our integral that we use to find the future value of continuous income stream in a little bit. And we're going to see some of these characters, but it's going to change a little bit. There it is. So before we talk about what all of this means, I'll give you a minute.
I actually learned this in my Accounting 255 class, but they give us a table instead of showing us how to come up with the future value. So this is kind of cool that you can actually calculate that.
That's neat. I have never taken an accounting class, so I didn't know that would come up then. But
You're lucky.
I feel like it's probably a useful skill.
Yes, it is.
Yeah, it's a neat thing about calculus in general, but things that come up in all sorts of different classes and fields, even if we get to use sort of shortcuts in other fields like a table, we can see how it works with calculus.
Yeah, a lot of the classes you can see there's some similarities that you come across that kind of intertwine and help you with one class versus the other. So
Yeah,
it's neat.
it is. Okay, so we have the same sort of starting off point. So if f of t is the rate of flow of a continuous income stream, so that's what we were talking about in the previous example. And if income is continuously invested at rate r compounded continuously. So as this income stream comes in, we're investing it in an account that has an interest rate of r and is compounding continuously. then the future value at the end of t years, so that's a capital T. So the difference between the little t and the capital T is important. So there are two statements here, and really we can use either one. It doesn't actually matter. But the first one matches our normal continuously compounding interest statement the most. So this P of T is like the principal. The big difference is that a principal is one amount of money that we invest at the beginning and it just stays there. Here we have a continuous flow. So instead of being one chunk, it's just continuously going in there. But that would be like the P and the P e to the RT. We still have the little r in there. The T though is different. So in our normal equation, the T is fixed. We put in an amount of money and leave it for T years. Here, the amount of time that the money is in the account depends on when we put it in. So capital T is now the amount of time that we're letting this all go. We're starting this continuous income stream and we're letting it do its thing for capital T years. The little t is our variable here. So our income stream is changing depending on little t. So that's just as time goes on. And each little bit of money that we put in is in the account for big T minus little t years. For however many years we're letting it go, minus when it was added to the account.
Will we see infinity for big T?
No, we won't.
Okay. Okay.
Conceptually, that could happen, but it's sort of a more advanced thing.
Okay.
So this first statement of future value matches with a few changes the normal continuously compounding interest formula. The last statement here is really the same thing. The only thing they did was take out the constant. So e to the r big T is a constant. Big T is going to be a constant number because that's how long we're leaving it. And the rest is on the inside of the integral. So it really doesn't matter which one of these statements we use, we will get the same result either way. So let's do an example so we can make sure we have all of the bits in the right place. So we're going to be using that same income stream from the previous example. So that vending machine is what we're using here. Okay. So continuous income stream from the previous example is invested at 4% compounded continuously. Find the future value at the end of the 5-year period. So we have this formula for future value. So in order to use that formula, we need to plug something in for f of t. We need to plug something in for r. And we need to plug something in for big T. Little t stays as it is. Whenever we're doing an integral, we have a variable. because the income is changing over time, that little t is expressing that change of time. So little t is going to stay just as it is, but everything else we need something to plug in. So f of t came from the previous example. My r got a little close there.
0.04 for R.
Exactly, 0.04. So it's really important to put the interest rate as a decimal.
And I assume 5 for T.
Yes, exactly. So 5 years is the amount of time that we're watching all of this happen. The vending machine has this continuous income stream and it is being continuously invested into an account. So that's 5-year period is what we're looking at. So once we know all of that, it's really just a matter of putting it into the formula and plugging it all in. So let's do that. So future value is, I'm just going to use the first statement, but you can use the other one if you want. So we need to be really careful here. It's easy to get confused with the e's. So this e that I just wrote is a part of the f of t.
So how come you didn't put 5 for the capital T?
Oh, because I forgot.
Oh,
Yeah, that should be a 5, thank you.
okay, no worries.
Thinking about the f, thank you. Okay, so we're going 0 to 5, since that's our capital T. We're plugging in that whole f of t, which is this whole 2500 e to the 0.05 t. Then our formula has another e. And this is e to the r, which is 0.04, times capital T, which is 5, minus little t. So
15,655.
let's find out. I don't know the answer yet. Just a note, you all know how to plug stuff into formulas, but just take care. It's easy to go a little fast and then forget something. So we just have to be a little careful plugging everything in. And I'm gonna, well, actually, yeah, let's just bring up Desmos.
It looks much different plugged in and written out than what the formula looked like.
Okay, so I'm opening the TI right now, but let's just look at it in Desmos first and then put it in the TI so we can see. So from the previous problem, I already have the 2500 e to the 0.05 t, which is the first part of this integral, so that's good. So I'm just going to add to it. So now we have e to the, and in our exponent here, we have 0.04 for the r, and 5 minus t. And we get 15,655.66. So that was in Desmos. So when we plug it into Desmos, it can look exactly as it's written in the formula. So let's just bring up the TI because plugging stuff into that can be trickier.
I was able to plug it in without any brackets except around the 0.04 minus the t,
Hmm.
and
Yes.
it went through.
Okay, good. So if you have, so let's go over to math, number 9 is a function. So we're going between 0 and 5. So, oh, whoops, 0, 5, there we go. So our whole formula should go inside these parentheses. So we have 2500 e to the power is down here. So this calculator automatically brings our exponent up to an exponent. If you have an older version and it just does a caret for an exponent, you might need more parentheses around what's in there. So 0.05t is this exponent, and so I'm just going to use x. It doesn't actually matter what our variable is, so I can just use x instead of t, and that's fine.
How do you get it to the other variables?
You would have to do, you would have to use alpha in this case, I believe. So I could do alpha t, and now it's a capital T.
Oh, okay.
But it's just easier to just hit the X button. Fewer things to push.
I agree.
So if your calculator does a little caret for an exponent instead of bringing everything up there, you will have to put parentheses around the 0.05x to show that all of that is in the exponent. And then we have another e, which is 0.04 times 5 minus t, or x in this case. And we should get the same thing. So we can see that by continuously investing all of that, without investing, our income was 14,200-ish. And now we get 15,650. So that's 1,450 or so more.
So the difference is what your income increases when you deposit a new deposit?
The difference comes from the interest
Okay.
from investing it in that account. The 14,000 or so is just what the vending machine is bringing in through selling stuff. But then once we put it into the account, now it's earning interest continuously.
Okay.
And so that additional 1,400-ish is in interest.
Okay. Right.
Yeah. Okay, so those are our two of our formulas for this section. We have our future value, or we have our continuous income stream. Where did it go? There it is, continuous income stream to get just the income. And then related to that, we have the future value if we continuously invest that income as well. So we're going to switch gears to a different application of integrals now. Any questions about either of these concepts? Okay. So before I reveal what consumer surplus is and what the formula is, I'm going to attempt to draw a picture again. So we're going to have this function, P equals D of X, which is a price demand equation or function. So X is the number of units sold, or number of units we can sell. And P is the price per unit. So we have seen price demand equations in this class, especially when we're doing like revenue. We have the relationship between the number of units we're going to sell and the price that we're selling them at. So in general, a price demand equation is going to decrease in some way. So this is just some price demand equation. So if we're trying to sell things at a super high price, we're not going to sell very many, but when we lower the price, we will sell more. So in general, that's going to be a declining function. So what if, for some reason, we decided to sell this item for a lower price than people would be willing to pay for it? And so I just drew a P with a little bar over it, and that is called P bar. A lot of times in math, a bar over a variable is used to say this is one specific P. So P in general is talking about whatever the price is, but P bar is talking about this one price. So there are basically two functions written here. There's this price demand function that's decreasing, and then there's just this flat line, which is the P bar. So everything in between these two for just, oops. For just up to where those two lines intersect, that is called the consumer surplus. Surplus. So if we think about what's happening here, the price demand equation tells us how much consumers are willing to pay for something. So if we sell an item at this price up here, consumers are going to buy this many of it. But if we, for some reason, are selling this item for a much cheaper price, consumers are paying much less than they expected, which is why consumers are getting a surplus, because they are keeping more money than anticipated or buying more of the thing than anticipated. And so this difference in here represents that whole surplus. So the difference between these two functions tells the difference between price of what people are willing to pay and what they actually have to pay. And that difference in price is happening over the X values up to wherever that surplus ends. And that X value is called X bar. So the surplus, was there a question?
No.
Okay. this is kind of a weird concept. When we put it into the integral, it's not so complicated, but just conceptually, it's a little weird. So we're selling between 0 and X items, because that's where the surplus is happening. And the surplus is the difference in price for each of those items. It's just the difference in price is changing depending on how many items we're selling. So we have this weird shape that can only be found from an integral.
So is it like the integrals where we'll take the top price unit and base it off of the p-bar to get the area?
Yes. So this is an area, like an area between curves kind of problem, like we were doing in section 6.1. So here we're finding the area bounded by this top curve, which is the price demand equation, and that p bar, which is giving us that bound on the bottom. And then it's just 0 to wherever those two meet. So our integral, I'm going to reveal the integral now. Oops. So here is our consumer surplus formula. So we have if X bar P bar is a point on the graph of the price equation. So that is always going to be this point on the price equation. And we are looking at a price level of P bar. So we have price demand equation P equals dx for this product. The consumer surplus at a price level of P bar. So P bar is going to be that lower price. Consumers are spending less than they are willing to. And so our consumer surplus is the integral from 0 to X bar. So X bar is that X value where the price level and the price demand equation are intersecting. And we're integrating the difference between the price people are willing to pay and the price that they're actually paying. So this subtraction in the consumer surplus is where the surplus comes from. We're willing to pay d of x, but we only have to pay p bar, so we have that extra money from that difference.
I assume this is how they come up with like sale prices.
Probably.
Okay.
I don't actually know that for sure, but
It kind of would make sense.
yeah.
Yeah.
So let's look at an example. Oops. Wrong thing. Okay, so we want to find the consumer surplus at a price level of P bar equals $4 for the price demand equation. P equals D of X equals 20 minus 0.05X. We don't really need to worry too much about this. Sometimes we've seen this kind of thing before in this class, but this is just a way of saying the price is a function that depends on X, and here is that function. So to plug everything into our formula for consumer surplus, the only thing we don't know at this point is X bar. We're being told what P bar is, we're being told what D of X is, but we don't know what X bar is. So I'm just going to scroll out for one moment so we can see our graph again. So X bar and P bar is always a point on our price demand equation because it's going to be where that P bar intersects the price demand equation. So if we know P bar, how can we find X bar?
Isn't it the same? No.
It's the same point on the graph. P bar or X bar, P bar is a point on the graph, but they're not the same number.
Set them equal to each other and solve.
Yes. Yes. So if we say that P bar has to equal D of X essentially, because this is one curve and this is another curve, and to find their intersection, we set them equal to each other. Or we can think of it as we are just plugging in 4 for P, since that's our P bar. And we're setting that equal to our price demand equation. So X bar is whatever the X value is when our price demand equation is equal to P bar.
Is it opposite if you only have the X bar and don't have the P bar?
Yes, exactly. So if we had X bar, we could plug it in for X and then we could find P bar. So we will just solve this. And you get 320. So that's just a little bit of stuff we need to do to find everything that we need to put into this formula. And now we have all we need to find the consumer surplus. So consumer surplus is 0 to X bar times D of X, which is that whole function, 20 minus 0.05X, minus P bar, which was 4 dx.
$2,560.
Okay.
Oh, not 20. 2.
Oh, 2, yeah.
2,000. Sorry.
No, I totally heard you, and I just added a 0 for no reason. There we go.
You can be my personal banker if you do that.
So that's the savings of all of the people who would have purchased it at the higher rates.
Right, exactly. It's like the cumulative savings of this whole difference for all of the extra, all of these units of stuff that we're selling at a lower price. Cumulative savings to consumers.
Now, would that be divided by 320 for each person? Is that kind of how you would figure that, or no?
We can't, because if we divided by 320, that would imply that, so the 320 is the number of units we're selling. So if each person was buying 1 unit, then it would translate, but it's really by units. But if we divided it by units, it still wouldn't quite, that would be the average, I guess, the average savings per unit. But we know that these first few units are actually, we're saving more on them than the last few units. So we can have
right.
like sort of a sense of maybe average savings if we divided by 320, but it doesn't translate exactly that way.
That's why I don't buy electronics as soon as they come out, because they're at the top.
And that's exactly why we need this calculus, because if we were saving the same amount for every single item, we would again just have a rectangle, which we can just multiply 2 things. So we need calculus because of the change depending on the x. Yay, calculus. So this for consumer surplus, for consumers getting to save stuff. But producers can also have a surplus. So I'm going to draw this one quicker. So in this case, we're still going to have this price. We're still going to have X, the number of units that we are selling, and P, the price per unit. But in this case, we're going to have a price supply equation. So now we're looking at it from the perspective of the producer. So the producer wants to sell more stuff if it's being sold at a higher price. So our price supply equation looks something more like this, and it probably shouldn't actually be starting right with the origin, but that's fine. So the point is that it's going up instead of down now, because the producer wants to sell more stuff if it's at a higher price. So now we're gonna look at what if something happens where the producer now gets to sell stuff at a higher price than usual. So people are, yeah, I should really change this. We're not selling things at $0. Just fix that real quick. Okay. So now we're selling things at a higher price than we were willing to. So the producer is willing to sell stuff for this price down here, but for some reason, consumers are willing to pay this all of a sudden, or they're going to pay this. So now we have this area in here, which is really the same concept. It's just going the other direction, where we have that difference in price. Producers are selling it at a higher price than they expected. So the difference between those two things will give us that extra amount of money that the producers are bringing in, and we're integrating over that area where that increased price is happening. So right in here is the producer's surplus.
That's the amount of money that's going into their pocket, correct?
Right. So it's conceptually really the same type of thing. We're still going to have this X bar also over here. So we're still looking at that place where our P bar and the curve intersect, which is going to be called X bar. The big difference here is that we have to remember from Tuesday that if we're finding the area between curves, the top curve always goes first in our integral. So it's always the top minus the bottom. So these two formulas look very similar, but that is a key difference. Thought that I had these attached to each other, but I didn't. So the wording of this definition is pretty much exactly the same as consumer surplus. We're just switching out demand for supply and consumer for producer. But now our integral is 0 to X bar again, but now we're doing the P bar first, P bar minus S of X, so the price supply equation. So just switching that order there is important. So let's look at one example. So we want to find the producer's surplus at a price level of P bar equals $4 for the price supply equation, this. So again, we're not being given X bar, so that's the thing we need to find.
100.
Okay. So we subtract 2. Oops, that's the wrong thing.
10,000.
Okay, thank you. 10,000.
You're welcome. Then square root 100.
And because we don't care about a negative answer here, we're not going to be making negative 100 units of something. We only keep the positive answer. So X bar is 100. So now we have everything we need to put into our integral. So producer surplus is the integral from 0 to x bar, which is 100. Let me show that while I'm writing. P bar is 4, and here just be super careful with negatives and parentheses. We're subtracting this whole price supply equation. And so our producer surplus is 0 to 100. And you get 133.33. So we're going to do one more price or consumer surplus, producer surplus problem. Any questions about these two before we do a little bit more? Okay. So this problem, we have the price demand and price supply equations in one problem, and we're asked to find consumer surplus and producer surplus. And we want to find those at the equilibrium price level. What does equilibrium price level mean conceptually?
When consumer surplus and producer surplus are the same?
Almost. So we are not looking at consumer.
Difference between them?
No. It is when two things are the same, but not the surpluses.
It's when the supply and
X bar.
demand are the same.
Supply and demand are the same, exactly. So our equilibrium would be when these two functions are the same. So equilibrium equilibrium. So we have our price demand equation and price supply equations. So what we need, the only thing we don't know from our, or the two things we don't know from our consumer surplus and producer surplus formulas are X bar and P bar. So X bar P bar is a point. And if we're looking for the equilibrium between these two, X bar P bar is going to be where those two are the same. So let's look at it on a graph, and you can find this graphically. You can do it algebraically. It's not necessary though. If you want to, you're welcome to, but you don't have to. So let's graph those two equations. So our demand equation, demand equals 70 minus 0.2x. And our supply so we have our supply and demand equations. So right now this is not a good scale. We can see those two squished down here. So I'm just gonna change y to be 200 just as sort of a guess. And the bottom should be like -1. So that looks a little better, but we don't see where they're crossing yet. So I need to up the x a lot. So let's try 100. So that's still not quite enough. So 150 maybe. Still not quite enough. 200. Oops, too much. Okay. So really, we just need to be able to see that intersection between the two graphs. So we have our price demand equation on top, that's decreasing, and our price supply equation on the bottom, that's increasing. And the equilibrium point is where those two are equal. So that's when X is 150 and P is 40. So that point where they intersect is X bar P bar. Ah. Forgot, 150, 40. So that means that X bar equals 150 and P bar equals 40. We would get the same thing if we took this price equation, the 70 minus 0.2x, and set it equal to the supply, or excuse me, the demand equation, and set it equal to the supply 13 plus 0.0012x squared. And you could solve that with a quadratic formula, which is totally fine, but you can also just graph it. So before we finish this off, I'm just going to go back to the graph for a second, and I'm going to graph that P bar line. And actually, I'm going to change the y-axis a little bit. So let's do y is 6.5. So we can see a little better. And so now you can see here, so we have our price supply equation on the bottom, and that producer surplus will be between this red line at P bar equals 40 and that supply equation. And the consumer surplus will be between that demand equation and our P bar. So the question is asking for the consumer surplus and producer surplus, so we can go right into finding each of those. I'm gonna do today's in-class activity a little differently than normal. So I just changed the settings on the chat so you can only chat to me. So I would like you to calculate this consumer surplus and send your answer to me in the chat so we can practice doing some calculations. So our consumer surplus is demand equation minus P bar and just this one so I'm not overwhelmed with chats. You can chat just the consumer surplus. And then we'll also calculate the price supply. So you can do both, of course. You only have to chat one to me. That's nothing. So as those are coming in, I am just sort of drawing a rough sketch of those graphs that we saw, just so it's in here. So we have our S of X. We have our P of X. Well, this one was just a line. D of X. So I'm just going to plug producer surplus in while people are getting that consumer surplus in the chat. Oops. Ah. Shoot. Okay. Struggling. Okay. So I got 27 for producers surplus, 2,700. And enough people have chatted 2,250 that I believe that. I haven't done that calculation, but. So this is our little graph. So graphically, we see up here is the consumer surplus because people were willing to pay more for a product and they were able to pay less. And down here is the producer surplus because they were willing to sell something at a lower price, but they got to charge more. So on this kind of problem, you may use the graphing calculator or Desmos to find that equilibrium point. And actually, you can also use it on these regular problems as well. We were finding X bar by plugging P bar in and solving. But I know that you know how to solve equations like this. So you can also find X bar from a graph if you want to. What I want to see on these problems is that you set up the integral all correctly and got the right answer.
Will these formulas be on the test?
Yes, you will be provided all the formulas necessary for the test.
Awesome, thank you.
You're welcome. So, speaking of the test, I'm just going to briefly talk about that. So we are in a pretty good place at this time. We have 4 weeks left in the term. And so we are going to do, we have a little bit more of class today, but we are done with chapter 6 now. So on Tuesday, so there's going to be a homework due next Tuesday based on this week. Next Tuesday, I will give up to 20 or 30 minutes of class for questions about the test. So if you have questions that you think of as you're studying for the test, which is on Thursday, you can ask them at the beginning of class on Tuesday. We are going to continue on in chapter 7, but we will have time for a little bit of question time. So if you have questions about the test 4, bring them to class on Tuesday and I will answer them. So all of the information for test 4 is up in the week 13 module because that's when test 4 is. Info guide, I put up a review sheet for chapters 5 and 6. There's also a practice test with answers, and then the actual test will be available on Thursday. So this will be an in-class test, just like tests 1 and 2 were. So we cover up to chapter 7 in this class, and we won't finish all of chapter 7. Chapter 7 will not be on a test other than the final. So the tests, chapters 5 and 6 are our last chapter tests. Then we have a little bit more for chapter 7, and then we will be done with the term. So I want to do a tiny bit of chapter 7 today as just an introduction, but there's a couple of things I wanted to mention. So I said we're not doing any more of chapter 6, and that's true. There are 2 more sections of chapter 6, and both of them are integration techniques. So in this class, we are using the calculator for a lot of the integrals. You do have to do some by hand from section 5.5. But integration has all sorts of techniques. So I just wanted to very briefly mention a couple of them in case you are feeling like maybe I should do more math and take regular calculus if you haven't gotten enough yet this term. Integration by parts comes from the product rule of derivatives. So our product rule, we usually use F and S as first and second for the product rule of derivatives. But U and V are a super common one as well. So if we take the derivative of U times V, we get U times the derivative of V plus V times the derivative of U. And if we integrate this, going through this quickly because it's not something you need to know, but it's just a little fun FYI. So this is the product rule of derivatives, but if we integrate both sides, one really important thing to know through calculus is that derivatives and integrals are opposites, so they undo each other. On this left side, we have the derivative and we took the integral, which means we're left with what we started with, uv. On this other side, we now have 2 integrals. If we have 2 parts added together in an integral, we can integrate them separately. Something neat is that dx works just like a number, which means these dx's cancel each other out. And so on the right here, we have u dv plus v du. And so those are differentials. Remember when we've been doing substitutions, we can have d whatever our variable is. So dv is the differential of v, du is the differential of u. And integration by parts rearranges this equation by just taking all of this part and subtracting it over to the other side. And we have this nice little formula for doing integrals in which the integral we're trying to calculate, which is on the left side here, has one function multiplied with the derivative of another function. And if we have that particular format, we can use this rearranged version of the product rule to calculate it. So you don't have to use this formula in this class, but this is just to show that integrals come in all sorts of forms. So this probably looks pretty weird as it is, but if we have an integral where we want to integrate a function and the derivative of another function, which actually comes up quite a bit, we have this nice little formula to do that. Integration has all sorts of different rules and formulas and methods. So section 6.4 is about other integration methods, which I'm not going to write anything here. But it's basically about approximation methods. A lot of functions are not that nice to take integrals of. And so there are all sorts of ways to approximate integrals using different things. So we saw the Riemann sums where we're using rectangles to approximate integrals. We can do that with trapezoids that have like a slanty top. And there's all sorts of numerical methods. So if we have a function that's not a nice curvy shape like we've been working with, you might have to do other integral stuff. So the conclusion of all of this is that integration is pretty messy. And if we go further into math, if you do want to do lots of integration, there's all sorts of different ways to do that. But for us, the important part is understanding how it applies to our applications. And so we can use technology to help us get there. Okay, so that's my little spiel on the end of chapter 6. So if you glazed over for those last few minutes, that's totally fine. So chapter 7, I just want to talk about real quick today because the first section is pretty short. And that is functions of several variables. If we are looking at a graph, normally we have functions of x. So y equals f of x is in 2 dimensions, just a flat plane. So we're going to be adding another variable in this last chapter. And that is if we imagine now a z-axis. So I basically push the x, y plane over so it's lying flat, and z is coming straight up out of them. So now we have 3 dimensions. And all of our functions are going to be z equals f of xy. So our functions will now have 2 variables. I guess technically 3 variables, but the function part will have both x and y in it, and that will always equal a z value, rather than a function having just x and that equaling a y value. And I'm not going to draw a 3D thing right this moment. We'll see some pictures and graphs later. But on this 3-dimensional coordinate system, we can have like surfaces instead of just lines. We can have 3-dimensional shapes. We could have a ball. We can have all sorts of things. So that's what we're going to be working with for the end of chapter 7, or the end of this class in chapter 7. And so just to sort of tie this into what we have been doing, we don't necessarily, you don't necessarily need to write this example down. We're going to come back to this concept next class. But so suppose a company produces one kind of kayak with a cost equation, C of x equals 600 plus 90x, where x is the number of kayaks produced. This is the kind of thing that we've been talking about since the beginning of this class. So when we talk about functions in several variables, graphically, this is what we are looking at rather than a plane. We have now 3 axes, but we actually use multiple variables all the time in the real world without thinking of it as a graph. So if that same company, they decide to start producing an elite level kayak also. So now they have 2 kinds of kayaks. So now their cost equation is C of xy equals 800 plus 90x plus 120y, where x is the number of standard kayaks produced and y is the number of elite kayaks produced. So when we talk about functions in multiple variables, this is the kind of thing that we're working with when there's more than one thing changing. It's probably pretty uncommon that a company is just making exactly one thing only, which is what we've been talking about this whole time. So now we're expanding this to talk about they could be making more than one thing. And if they decided to make one more kind of kayak, we would just add another, whoops, I missed where I was trying to go. If they decided to make one more kayak, we would just add one more variable in there. So we can have as many variables as we need to express the system that we're working with. And so the question here is, what is the cost of producing 15 standard kayaks and 10 elite kayaks?
So plug and solve.
Exactly. So the notation, so this is mostly sort of an introduction to notation of multivariable functions. We would say 15 is the number of standard kayaks, so that's our x value, and 10 is the number of elite kayaks, so that is our y value. So we plug in these, we say C of 15, 10, because those are our x and y, and we would exactly plug them in as we're seeing them. And
3,350.
3,350?
Yeah.
So really, this is not new, it's just more of what we already know. We know how to take a number and plug it into a function. Now we're just adding variables that we can still plug into for that function. And so this is what we have to look forward to the end, for the end of this course, doing stuff in more than one variable, multivariable functions. So I will not try to get ahead of myself today. We will pick this up on Tuesday. So have a good weekend and I'll see you next week.
Thank you, Madeline. Have a great day.
You too. Thank you.
Thanks. Bye-bye.